So today we will go through how you can combine the two languages we have talked about in this course. Sometimes it's also called mixed language programming, but in this case it's just we are going to just go through how you do with Fortran and Python. If you look at Python, you can link external code using something called extension modules. And many of the modules that we have been using during this course, for example, NumPy and Matplotlib, are actually implemented as C code. And there is a special API that you can use and to create these extension modules. And when you have compiled these modules, they can be used just like any other Python module. There is no difference. It's almost indistinguishable. And a lot of the Python runtime libraries also implemented like extension modules. And you can do that by installing the development environments from the development libraries for Python. And then you implement something like this. So here in this case, we implement a function that can sum. And then you have to use a special syntax here to implement it. Here is the actual implementation here, C equals to A plus B. And then we return the results. And you see you always have to kind of use some of the functions here to communicate with the Python interpreter. And then you have to make sure that you export what you need in your module. Do some other things here to initialize the module. So it's not and then we have another thing. We are going to use Fortran. So we need to link with this or use something that can link with Fortran. But there is an easier way to do this. So there is a tool that comes with NumPy, and it's called F2Py. And that tool parses your Fortran code and generates this extension code automatically for you. So it generates C code, which you can build and link to a Python extension. It's a command line tool, and it compiles and links the modules automatically. So what you get afterwards is a special, if you're in Linux, you get the PyD something module or SO file. On Windows, you will get the PyD file with a name, a long name. There are some drawbacks with this. It's because it first parses your Fortran code, generates C code, and then compiles it. You can get a lot of strange error that can be related to your code, but can also be related to how you compile the C code. So before you use these tools in a more for your own projects, make sure that your existing code works. So you don't have to double debug. You need to kind of focus on your Fortran code or the linking here that it works. So we'll start with a simple example here. I have this function here in Fortran. Basically what you saw in the Python tool here. 3 parameters here, A, B, and C. And to use this tool in the right way, we should use these attributes intent in, intent out. These you can already use in your Fortran code without no problem, but F2Py looks at these attributes to generate the correct Python code. So for example, input variables will be placed in the function argument list of Python, and out will be on the return left side as a return variables. And here we just do the operation here. And then we have to execute F2Py. So it looks kind of strange in this notebook here, but if you have installed the F2Py on your own machine, Linux or Mac, you can just type the command here, F2Py. This exclamation mark means that we call this command from the command line in the virtual machine running in this server here. So F2Py, then we give it a module name. So this is the name of your extension module. And then we give it what it should compile. So C stands for compile and M stands for module. So let's run this. Now you can see here it generates a lot of output here. And ignore that is just because I have a tab character in my code, then it complains because it's not really Fortran. but then the important thing is that you get this here. And this is the extension module. And you don't have to remember all that stuff here. That is just that this extension module is compiled to CPython, which is the normal Python, and it uses version 3.10, and it's for x86-64 architecture. So this is actually a binary module in machine code. So you can't take this and run it on a machine that has an ARM, for example, ARM processor. So this is just kind of identify this is the architecture. And also Python looks at this when you import that to see if it's compatible or not. So then we can use this module, and we do. So the module name we gave it, we can import. So import simple, that will import the module, and then we can actually check what the module does, because FTPy also generates documentation automatically. So it actually, in the documentation, it says which parameters are here and what type they are and how you should call them. So let's just run this. So you can say this module simple is auto-generated F2Py, and it contains the function simple. And here you can see, because of the intent out and intent in, it rearranged our function here. So the intent in will be parameters on the right side of the equal sign, and the return value was intent out, and that was the C value here. We can also print the documentation for the function. Then you do simple for the function, and doc, and that will produce the documentation for the function. You can see here that we have A and B, these are float, and C is also float. And you can see when we declare the function here, we have real here. And then we can try the function here. And now we went from Python to Fortran and back. This is really simple, just using scalars, but we can use arrays as well. So let's implement matrix multiply in Fortran and expose that function to Python. So here we need to be more specific here. We need to provide the sizes of the arrays going in here. So we have A has rows r, s, B is same number of columns as s, and then some rows here as a's number of columns, and then t here we provide as well. And then we have C that can be constructed with r, t. And then we can do C matmul AB, and then C will be returned here. You can see also the intent in, and out. And I usually start by printing documentation here to see that everything went okay. So let's see here. It's auto-generated with F2Py. It's C equals to matrix multiply AB. And now you can see here it says that we have R shape here, and it figured out the sizes of the arrays coming in. And then the really nice thing, if you do look at the function declaration, you can see there is a square bracket around the size variables. That means that you actually don't have to send them over. The generated code will automatically send the correct sizes over to your function. So you only have to call your functions with A and B. And here you can also see that you have A is an input rank 2 array, F with floating point with bounds R and S, B is input rank array with bounds S and T, and then you have C is with bounds R, T. So let's see here what we do. One thing that when we pass arrays here, I touched upon it before with the array storage, that you can have column-wise and row-wise storage. Because NumPy is implemented in C, it uses stores row-wise, and Fortran has column-wise. So we need to tell NumPy to generate arrays using Fortran ordering. And you do that by specifying this parameter here. Order equals to F. and you do it on all the arrays that we pass to Fortran. And then it will pass it by reference. So F2Py is really good at, if it notices that you have an array that is not Fortran, it will do a copy and transfer over the correct one. But it's better to give them directly as Fortran array, because then there will be no copying overhead. So let's see here, we can run this. But one thing here to notice is that I use ID here to identify the arrays here. So C here going in has ID 432 at the end, and C going out has another array, another memory location. And that is because we put intent out, and the equal sign here will actually generate a new NumPy array. So this will not be used. So you'll get another creation here, which you can it's okay, but otherwise we need to kind of make it, if we want it more efficient, we need to make another implementation of the matrix multiply function that can take C as an array by reference instead. So we go and modify here. So instead of saying out, we said in out. Then we tell the F2Py compiler that C here will be used for this here, and don't create an additional C. Store the results in the incoming C variable. So let's compile that. Now the function becomes a bit different here, so you can see there is no left side. C is on the right side now. And also we can see it more clearly here. A, B, and C as input, and now left side. And you can see also that you have in and out here for the rank array here. And now we do it like this instead. We create C here, and we want to store the result in C. We create as an order F array. And if we run this now, you can see here that it's the same array. So this call here has the least overhead. There is no copying going around. It's just passing the arrays over as pointers basically to the Fortran code. So this is the most efficient way of doing it. For smaller things, it's perhaps not so important, but if you have really large array, you really don't want to be copied in the call. Now, what we have done now up until now is we put the subroutines in a separate compiled, but it's also perfectly fine to actually compile modules, and then you will get an extension module with sub-modules in it. So every module you compile and integrate into your extension module will be a sub-module to that main extension module name. So here we have a matrix module. I have my two functions here, matrix multiply and matrix multiply 2. And I can just provide it here as a single source code file, and I can name it matrix here, but perhaps I should do it otherwise it becomes my matrix, which is a bit. So let's compile it like this. Oh. So you can see here, okay, I call it. Yeah, and then it has a module called matrix init. So this is the outer module. You always get a kind of a module when you import it, or when you generate it, that is called the same name as the extension file. And here you can see I have internal module called matrix in that one. And then we can print it here. You can see here now we have 2 functions in this module here. Then you can do from myExt import star. We'll skip that. Yeah. So what I usually do when I have this, if I have my source or Fortran source code is only modules, it's sometimes beneficial to use the non-recommended way of importing by doing from myExt import star. Then I will not have to specify the myExt prefix on everything. I import every module that is inside here. And then I don't have to have myExt in front here to call it. And here you can see also, if I have loaded a module, you can actually unload a module using delete, the delete function. So this is quite useful. One thing that I recommend you to do when you are working with your own code is that you can, when you run all your code through F2Py, it's not always that you can get everything to compile. So sometimes there are things in your own code that is not compatible with F2Py. So in this case, my recommendation is that you create the code that you don't want to include in F2Py. You create a library, put that code in that library, and create a wrapper function on the functions you want to expose. So you create a special module that interfaces with your undercode, and that is the one you convert to an extension module. So you do it in 2 steps. Create a library with your functions, and then you link your, when you have F2Py, you can add a linker to link with a certain library, just like you do when you compile. So this is a high-level one, and I will show an example now, a more kind of useful example that does some image processing. So let's see, I can go to here. So I did an experiment here to see to do a very simple imaging filter. First, I implemented the filter in Python here. So it's a blur filter. And it takes an image here. You can give a kernel size. It does. I think this is the way I could find the fastest way of doing it in NumPy. So try to avoid loops, but somewhere here in this there is a loop, so you can't avoid that. You could also have done a very simple looping over with the kernel, but I try to get it as fast as possible in Python. Then I have done filters.f90 here. That has the same thing. You have an image here, you have a kernel size, and then you have an array here for the filtered array. Here I also used ISO-C binding here to define the corresponding C doubles here, so I get the correct things over. It's not strictly required. And I also try to get the Fortran code as fast as possible using OpenMP. But that's the details here. And then I have, well, let's say where I have my image processing here. I have done some utils here which you can actually compile your code directly in your Python code. So in this case I do F2Py setup, and that is to configure the search paths, especially for Windows, and then compile. And I want an extension module called filters, and you can list your source code files here. So I try to compile this one here. And then I load the image from file. And then I create a Fortran array here. set the parameter here for the kernel size, and then I do measure here how long does it take to do the blur in Python, and then I create a new array here, filter image 2, that I will pass the Fortran here, and in this case here I will I have to do it several times here to get a good time here. So I loop over here and I call this filter function several times. And then I also, there is actually CV2 has the similar function built in, so I compare with the built-in function in OpenCV library, just to kind of have some. And then I plot the filters here, the images here. So if I run this, it will start by compiling the filters module and then run the different parts here. So now it compiles the filters module. And it took 0.388 seconds in Python. And now it does it several times in Fortran here. So that's why it takes a bit longer. So you see, it is difficult to see here, the blur, because it's a large image here, but you get the same result in all of them. And you can see here that OpenCV, apparently, I'm suspecting it uses some GPU function here, so it's a bit slower. But you can see I got from, but this is really slow. Okay, I had to check. It should have been faster. It could be, yeah. Okay, let's try it again. It could be that I'm running something in my computer here as well. So I got something like approximately like the CV2 here when I run this here. I think it's because I'm recording at the same time here, so it's a bit. But basically, using Fortran can give you quite a speed up by using F2Py. So if you figure out that, oh, this Python function here is really, really slow, perhaps rewrite it as a Fortran subroutine, compile it, and just use it as an extension module. And I can show you here what I did for the setup function here in. So this MF mix here, which you have that available as well. And this is here for, it's really annoyingly complicated to build on Windows. So that's why I have some extra things here. Here I have some optimizations flags as well. You can give that when you compile. You can also say that I want to use OpenMP. And basically I set up everything here to be able to compile it. I also add here on Windows here that where it should, where the binary files are for the Fortran compiler. But then you add a compiler. So here you can actually compile it and you can actually set all the optimizations flag you like, even OpenMP, to give a multi-threaded version of this extension module. But if you are on Linux on Mac, you can use the F2Py command directly on the command line like this. On Windows, you need to. I will update my Fortran book here with how you should do it on Windows as well if you're running Windows. If you're running in the VSL environment of Windows, the Linux, you can use the same as on Linux as well. So it's very useful for accelerating Python. So the final part of this lecture here, I would like to talk a bit about environments. And I'm not sure if you have used Anaconda for a long time. At some point, you get into the situation where you can't install any packages anymore, and you have to kind of start from the beginning. And at some point, I discovered that there is a way of solving this problem that is actually really good also for scientific reproducibility, and it's called environments. And I can just show you here. I have Conda env list shows me the environments I have now in my computer. And I have here, you can also see that if you open a terminal with Anaconda, you get this base here. And base is the base environment that you always get when you start up Anaconda, and that contains all the packages if you have a full Anaconda install, or just the basic ones if you have a mini Conda Forge installation or mini Conda, something like that. So you can see here I have base activated. I can switch using Conda activate, so compute environment. Now I'm inside the compute environment, and if I type Python -v here, I get the version of Python here is 3.10.14. I can do Python or Conda deactivate, and then I do Python -v. You can see here I have another Python interpreter. So what you can do with an environment is that you can create for every project you have, you can create a clean environment for your Python. You can also, if I have requirements that, okay, the package I use have a requirement of having Python 3.8, for example. You can create an environment like that. So for example, I can do Conda create -n for the name of your environment. I will do test1 here. If I just press enter here now, I will get a completely empty environment. So there's not even a Python interpreter. So usually the thing I do, I always give a start with Python equals to 3.8. And then I press enter here. I'm using Conda Forge, which you should do. We don't break any license agreement.
I should make the switch.
Sorry?
I should make the switch.
Yeah. So my network connection is not super fast here. And now I see here that it suggests a basic package set here. So now we get kind of just the packages you're required to run Python, but also be able to install packages. You have the pip command here to install packages with. The Python here, there are some other things that are also required for running. And then I press yes here.
Do you find the packages before all the new are going to be installed?
Yeah, you can after the Python equals to, you can add more or add package names. I just want to show the basic empty environment. So now you can see also it says that to use this you have to activate it. So that one thing I have done many times by mistake, create an environment, start installing packages, but I forgot to activate it. Then you get everything in the base environment. So the first thing we have to do is do Conda test1. Now you can see here Python -v. We have 3.8. And now I can do a Conda install numpy matplotlib. So my recommendation also, if a package is available in Conda, use that first. Because usually, for example, for NumPy, those are compiled with optimized libraries. And if you do pip install NumPy, you get a different NumPy than you have in Conda. So the Conda one is usually faster. But there are a lot less packages in Conda, so for many packages you have to have pip as well. And that is also really good thing with environments. You can mix Conda and pip. And you have a self-contained environment that you can't mess up. So if something goes wrong, yeah, you just delete that environment, restart again. And then you can see Python has there's a lot of dependencies. And yeah, I mean, you can see here that you have libblas, liblaupack, and those stuff, and somewhere you also get some MQL stuff as well. Okay. Yeah. So if I do a conda list, you can see all the packages I have here in my module. And you can see also the package names are 3.8 here. That means that there are packages specifically for 3.8. So if I do Python here, I should get the 3.8 version, yes. I can do import numpy SMP. And I have all the things here.